Greetings, George Nawczyk. Today is early Tuesday morning, March 26, 2019. In this video, I'm going to be discussing some more geometry on a curved earth. This has to do with the ability of a human to detect whether or not, if you had several objects out in the distance and some may be leaning away from you, whether or not you can easily detect which of the objects are tilted or leaning away from you. The motivation behind this is some recent discussions that have been on the Flat Earth forums. I normally don't try to do any Flat Earth videos, but this particular topic also has some very nice geometry associated with it, so this is more of a math geometric video, but it ties into some of these discussions on flat earth. And what that has to do with is, say you have a curved surface of the earth and you're an observer here and you have a tower of a certain height that's vertically aligned, and another tower, say, is 69 miles away of the same height and also vertical with respect to this point on the earth. Well, given that the earth is curved, this object is tilted away from the observer at this point. Well, how much of a tilt is there? Well, given the size of the earth, the radius being 3,959 miles, you find through simple geometry, I've discussed this in some previous videos, that at 69 miles away, the expected tilt is only 1 degree. That is, if we were to slide this object parallel and bring it to align with this tower, that the angle here is 1 degree for every 69 miles. So if you're double the 69 miles, at say 138 miles, then the amount of tilt would be another 1 degree and 2 degrees with respect to the observer 138 miles away. So the tilt is very, very slight. So the question is how much tilt do you need before you can really detect it? And that's what we're going to be discussing here. So, for example, I have 3 poles, say, set up. And one of the poles is vertical, the other 2 are tilted. So the question is, which is vertical, which is tilted? If I turn it to the side, you can easily determine which they are. One of the peg poles is tilted at 7 degrees with respect to the vertical. The other is tilted at 20 degrees with respect to the vertical. Again, when you're looking at them direct on, it's very difficult to tell which is tilted and which is not. And that's what we're going to be discussing in this video. And I'll also show you some actual measurements with much larger poles, using 10-foot long poles, 3 of them, and sighted 441 feet away. And I've made measurements using a Topcon GTS 3C theodolite, and I will be showing the video of that. Basically what I'm going to be doing here is, there's going to be several parts to this. First, I'm going to give you the results of some of the geometric theory, and then I'll go to the video of my actual measurements this past Saturday out in the field, and then I will come back and present the results from the measurements, and then in a part 2 of this, I will discuss the theory and go through all the mathematical derivation of the equations that I came up with. I'm not going to put them in this part 1 because it would drag the video out too long and probably lose the interest of many viewers. But if you're interested in the mathematics, the part 2 will be discussing that along with some additional measurements that I made. So we'll get started here. Is the theory on this is as follows. Is here, say we have two poles side by side. One is vertical and one is tilted. As we can see, here's the front end view, here's the side view. Well, as an object tilts more and more, here we have two poles side by side. Now as I lean this pole, we can see that there's a perceived height difference between them. This pole that's being tilted appears to be a little bit shorter than the vertical pole. So we have to ask ourselves, how much shorter does it appear with respect to the tilt angle? Well, this is what this illustrates. Here we have a vertical pole, and here's the pole that's tilted, and here's the side view. The amount that it's tilted we'll call angle theta. The amount that it's tilted from vertical. Well, there's a perceived height difference. That height difference we'll call d. The perceived height difference. The height of the vertical pole and the pole that is tilted, the lengths of those poles is h. As we tilt the pole, the length of the pole doesn't change. It still remains at h, but it just appears to be shorter because it's tilted away. The relationship between the tilt angle and the perceived height difference, d, is very easily determined because we have a triangle here. If this is the vertical pole of height h, and this is our tilted pole, it has also length h, and the difference in the distance between them now, because one of the poles is tilted, we'll call this x. That is the distance, horizontal distance from the vertical pole over to the tilted pole, and the tilt angle is theta. Well, the relationship is this, is here we have the length of the vertical pole, but the length of the tilted pole appears to be foreshortened if we project it over onto the vertical pole. This length here, given by trigonometry, is h, the length, the hypotenuse, times the cosine of the tilt angle. That's this length here. Well, the perceived difference in height we call d, so this is just d is h minus h times the cosine of theta. So we could write this as h times 1 minus cosine of theta. Okay, that's one of the relationships. The other relationship is if we look at these poles from a distance. Here we have an observer out back away from the poles, say a distance r. Then the observer is going to see the height of the tilted pole, the perceived height, and the perceived height of the vertical pole. Again, this height difference we call d, but if we go back to the observer's eye, we see we form another triangle here. Well, the relationship is whenever you have a length r and you sweep out an angle, say called phi, you sweep out an arc length s, and the relationship is s equals r theta, or phi, where phi is in radian measure. Well, what we need is a straight line distance. That is this chord distance here. which we call D. Well, D is related to S, and the difference between them is very, very slight if the angle phi is reasonably small. For example, if I have, this is the diagram that I have here, call this phi. All right, and this is our angle phi. So we have a radius r that we're sweeping out an angle phi. We sweep an arc length out s, and we want to really know what d is in relationship to s. Well, d is approximately equal to s if s is the angle is fairly small. What we mean by fairly small is if the angle is 10 degrees, the amount of error that we pick up between d and s, d is smaller than s by 0.127%, very small, almost 1/10%. And if the angle sweeping out is 20 degrees, then the percent error in d in relationship to the arc length, d is only shorter by 0.5%. So the angles that we're going to be dealing with when we're measuring is well under 1 degree, and with 1 degree this error is extremely small because look at it goes as the angle squared. So if we get down to 1 degree, the error in 1 degree is going to be smaller than 10 degrees by a factor of 100. So the error then, if we talk 1 degree, then the percent error is going to be on the order of negative 0.00127%. Negligible, not worth worrying about. So we can then, for all practical purposes, say then that d, this difference in perceived height, is just r times the perceived angular measure difference between the heights of the pole. So these are the only two equations that we need, and if we manipulate the equations then we will find that we also have these other relationships. Is that if we want to know the relationship between the tilt angle and the perceived angular measure that we measure on the height difference between the poles, are related in the following manner. That the tilt angle is the arc cosine of 1 minus r over h times the perceived height difference angle, phi. This is an exact equation. Now, we can make some approximations and make use of calculus, which I'll show you in the other video, is that angle theta in radians is equal to twice the distance, the measuring distance to the poles, times phi given in radians, divided by the height of the poles. Now, if we want to express this in degrees, use theta in degrees rather than radians, this comes out to k times the square root of phi in degrees. If you express phi in degrees rather than radians, then k is 360 divided by pi times the ratio of the distance the poles are from the observer r divided by the height of the poles. So this is an approximate relationship that's very good, has very little error. So in relating the angle theta of the tilt angle to the perceived height difference angular measurement phi. This is the relationship. Now the uncertainty, if we say have an uncertainty in the amount that we can determine phi, which we will be using a theodolite to do. Instruments aren't perfect, they have some degrees of uncertainty. So the degree of uncertainty in theta in degrees is k over 2 times the uncertainty in phi divided by the square root of the measure of phi. And the k is the same as the k here. Now, I'll show you the instrument that I'm going to be using, and then we'll get some estimates on the numbers, and then I'll show you, we'll go to the video where I actually did the measurements using 10-foot poles. Here I have my Topcon GTS 3C total station theodolite. The total station means that this is much more than just a standard theodolite. It also has a laser inside it that, when used in conjunction with this retroreflector or corner reflector, can measure distances accurately, very accurately, to well within a centimeter over a kilometer distance. And it also measures vertical and horizontal angles very accurately, to within 5 arc seconds. You can see here some readout, and as I turn the theodolite, it reads out right now it's reading out horizontal angles, and then you can switch the display to measure vertical angles, and it measures both the horizontal and vertical angles to within 5 arc seconds. The resolution of the human eye is about 72 arc seconds. That's 0.02 degrees. So this theodolite is 14.4 times better than the resolution of the human eye. So it improves our capability of measuring angles by over a factor of 10 from just using the naked eye. And this I'll be using to measure the angles, perceived angular difference between the pole heights, and compare it with actual measurements of the poles directly, and just to show that this theory does work out exactly. Here is a summary of what we have so far. Here are the theoretical equations for relating the angular tilt angle to the perceived angular height difference between the poles, where phi in degrees is the perceived angular height difference of the poles, and theta is in degrees of the tilt angle. K is this factor here that I just described, and this is the equation for the uncertainty in determining the tilt angle from the perceived height difference, where we have a certain amount of error, delta phi in degrees, of the perceived angular measure of the or the angular measure of the perceived height difference. Now, for the tests that I'm running, I ran the distance meter, and it gave me 441.38 feet, which is 5,279 inches, or 97 inches. The height of the poles is 10 feet, or 120 inches. And for this Topcon GTS 3C I just showed you, the uncertainty in the angular measure of the perceived height difference of the poles is 5 arc seconds, which is 0.0013889 degrees. And if we put all these values in for R and H and put them in these equations, Our K value comes out to 71.1215. K over 2 is half this, or 35.561. And we put that in these two equations. So our tilt angle measured from the perceived height difference in angular measure phi is 71.125 times the square root of whatever this angular measure is for the height difference, and then the amount of uncertainty in this particular tilt angle measurement using the Topcon limitation of 5 arc seconds gives us 0.04939 divided by the square root of whatever this angular measure is. Now, representative numbers for this is if, say, we measure the perceived height difference in angular measure of phi of 1/10 of a degree, then the poles have to be tilted by 22.49 degrees. That's what we'd get from this distance of 441 feet away. If this pole here is tilted by 22.49 degrees, then the perceived angular measure will be 1/10 of a degree for that height difference. And the amount of uncertainty using the 5 arc second uncertainty, the amount of uncertainty in this measure will be 0.156. So very small. This could be 22.49 plus or minus 0.156 degrees. Now, if we happen to be measuring with the eye, if we could do with our naked eye using the resolution of the eye of 0.02 degrees, then the amount of tilt angle that we would have between the poles is 10.06 degrees with 0.349 degree uncertainty, say if we had an uncertainty of 5 arc seconds in our measurement. Well, what this tells us is right off the bat that at this distance of 441 feet away, looking at poles 10 feet in length, that we would not be able to detect a tilt angle of anything less than 10.06 degrees. That's what this is telling us. So if, for example, these poles were tilted, the pole was tilted by 5 degrees, that would fall below the resolution of the human eye to detect. There wouldn't be any way to detect a perceived height difference between the vertical pole and the pole that is tilted. Now, for the Topcon GTS 3C, this is our limitation. We can measure phi degrees down to 0.0014 degrees, which would give us a tilt angle of 2.66 degrees and an uncertainty of about half of that. And that's because we're getting down to the limitation, the capability of the Topcon. So this would be a 5 arc second measurement, and if we happen to just jump up 1 degree or one numerical value in the last digit, which is 5 arc seconds, say go to 10 arc seconds, we would pick up 1.3 degrees of angular uncertainty in our theta. So with the Topcon, even then, if the at this distance, if the pole is tilted from vertical by less than 2.66 degrees, even the Topcon wouldn't be able to tell the difference because of its 5 arc second limitation in measuring the vertical angles. So these would be the limitations. This is the human eye limitation, so we would not expect to be able to detect a tilt angle less than 10 degrees, and with the instrumentation a tilt angle less than 2.66 degrees. So now we'll go out in the field and demonstrate this principle. Today is Saturday, March 23rd, 2019, and I'm setting up the test range for the pole tilt test. We're looking down the test range right now. I haven't set the poles up. What I'm first going to do is measure the distance from the camera on the theodolite here to where I'm going to have the poles set up, and as you can see coming into view is my corner reflector there that I have set up, and I'm going to measure the distance here shortly. I'll take the camera out and show the equipment. Here I've got the theodolite set up, and that's looking down the test range, and so we can get our coordinates. Right now it's indicating the satellites that it's acquiring, and we'll go to the positioning, and we're on WAAS averaging. So here's our coordinates of the theodolite, and I'll take the GPS with me down when I'm installing the poles, and we'll get the coordinates there. But right now I'm going to go ahead and measure the distance. I paced it off earlier. I tried to pace with 3-foot strides, and I got 153 paces, which puts it at 459 feet, and we'll see how accurate I was with the pacing. Here's the theodolite turning on. I've got to flip the, get our data. Now get it sighted in here. On the target. Yeah, it looks like the wind's moved the target a bit around. I'll now make a distance measurement here. Whoops. You can see that it's making a distance measurement. There we got 441.380 feet to the retroreflector. So pacing it, I had 459, so I was off about 18 feet trying to pace it. I'll make another measurement here just to reconfirm. Again, 441.38 feet. So that's our distance to the targets. I'll now show you what it looks like through the theodolite. I gotta put a hood over me. Okay, so here we go. So there's a retroreflector. Yeah, sighting through the theodolite. Things are a little fuzzy because I don't have them quite in focus. Try to focus it here. Okay. So there you see the retroreflector, and we're 441.38. Okay, now I'm downrange at where I'll be setting the poles up. Right here I have a marker board that has increments of 5 degrees that I'll be using for aligning the poles. And here are 10-foot poles. These are PVC 4-inch sewer pipes. And I've made a base here with a 2x4 to make sure that the pipes are all set up at the same height. You can see here that the bubble is on center. So the base is all nice and level. And here's the retroreflector that shoots a laser light back from the theodolite total station to measure distance. So we have that now done. Now I'll set up the poles so that all 3 are vertical. I now have The 3 poles set up and vertically aligned to be plumb. I had to pack snow around the base. The wind's kicking up and is moving the poles around. So luckily I have a snowbank here to work with and is able to keep the poles now nice and steady. Look now at our GPS coordinates. Here. We're at 48.61378 degrees north by 93.30622 degrees west at 1126 feet. Just take a look, see what we have for satellites at this point. Oh yeah, we've got good reception. A lot of good satellites. Okay, so now we'll go back to the theodolite and look at the poles. The theodolite is back that way. Take a look here. It looks like Con's down there waiting for me. Yeah, you can see the theodolite and the bicycle and Con there waiting. That's 441 feet away. So now we'll go back there and make our first measurement. Okay, we're back at the theodolite. I've got the GPS set up just to read the coordinates here one more time. We're at 48.61387 degrees north at 93.30803 degrees west and 1128 feet this time. Handheld GPSs just don't have very accurate height measurement capability. The latitude and longitude can be positioned within about 3 meters with this GPS, so it's not as accurate as the theodolite is for making a distance. Move the theodolite around. You can see that we have our poles there. I'll do the vertical positioning. There's our base. There. Now we'll look in the vertical. We'll look at the tops. And there we are. You can see that the tops are all aligned. They're all vertical. Now, look through the camera. So, all 3 poles are vertical, and again, they look to be the same height. Now I'll go and adjust one of them, or 2 of them. Here are the poles leaning. The middle pole is vertically plumb. The pole nearest, which appears to be on the right of the image from the observation point, is leaning at 2.7 degrees. And the one that will be at the left in the image is leaning at 16.5 degrees. So we'll now go look at it through the theodolite. Now looking at the test range, down range at the poles that are 441.38 feet away. The leftmost pole is leaning at 16.5 degrees. The vertical pole is in the center, and the rightmost pole is leaning at 2.7 degrees. Now it's very hard, almost impossible to tell the height difference between the vertical pole and the one leaning at 2.7 degrees, but we definitely can see a height difference at the 16.7 degree pole. Now we'll look through the theodolite and make some measurements. Okay, now we're going to look through the theodolite at the poles downrange and make some measurements, angular measurements. The theodolite measures vertical angles with respect to a true vertical. 0 degrees registered on the theodolite is downward towards the center of the earth along a vertical line, and then as you go from vertical pointing downward out towards a horizontal, 90 degrees is that horizontal. So we can see we're reading a little bit below horizontal right now, but I need to adjust the crosshairs so that I'm measuring the tops of the poles in the distance. Got to put a shroud here. The sun is bothering getting a good photograph. So looking now through the theodolite, we can see the 3 poles, and you can see the horizontal crosshair, and I'm going to adjust it so it goes to the top of the middle pole. And once I get to the top, then I measure the angle, and then I adjust the gotta get it here. It's really tough with the wind blowing. Okay, so we get it there. We make it's 89 degrees, 54 minutes and 15 seconds for the middle pole. And zoom in again. And you can just barely see a gap between the middle pole, which is vertical, and the rightmost pole, which is at 2.7 degrees. There's a little bit of a gap there. We'll move the crosshair down and get it to the top. And note, angular reading is 89 degrees, 54 minutes and 25 seconds. Then we'll do the same here on the leftmost pole, which is leaning at 16.5 degrees. So take the crosshair here, move it down. So there we're at the top. And note the reading. Gotta focus it in. We're at 89 degrees, 57 minutes, and 15 seconds. So from those readings we can get the angular size difference, the angular measure. Okay, now we'll go and readjust the poles again for a different angle and use the same procedure and get the angular measure. But again, let's take a look. We really can't tell the difference between vertical and 2.7 degrees. You just can't tell the tilt on that. But we can discern that the tilt at 16.5 degrees is noticeable on the height difference. That's the only way we can tell the difference. So you just can't detect if I go, say, down here where you don't see the tops, there's no way that you can discern any of the poles are leaning. until you compare the tops. Now here, coming up upon the poles, take a look again at the poles leaning, and then I'll change the angle on these. This is a line now perpendicular to the line of sight between the theodolite and the poles, and we can see that indeed they are leaning. The pole closest to me is leaning at 16.5 degrees. Center pole is vertical and the other pole is leaning at 2.7 degrees. Now we'll change the lean angle. Back at the observation point, after adjusting the poles, zoom in here, take a look at them, see if we can discern the tilt. Only by looking at the tops can we really tell that their poles are not all vertical. The left pole is leaning at 5.6 degrees. The right pole is leaning, has a tilt angle of 11.1 degrees. Again, there isn't any way to tell that the poles are leaning unless you look at the tops. If I cut the tops off, you can't tell that there's any lean or tilt to the poles. Now we'll look at them through the theodolite. Okay, now we're going to look at the poles through the theodolite. Again, we have the theodolite set up here. Get the bubbles centered so that we get an accurate reading. The bubble adjust is 30 arc seconds per division on the bubble. Okay, so now get the hood on here and we'll look at the poles. There we can see. Oh man, it's a little hard to get this all set up. Okay, here we go. Now we can see the poles, the tops. Okay, we'll get a reading at the vertical pole in the center. Okay, the reading there is 89 degrees, 54 minutes, and 25 seconds. 89 degrees, 54 minutes, 25 seconds. Okay, now we'll adjust for the left pole. So I'm going to move the crosshair down, as you can see, and we'll just catch the top. There we are. Vertical angle reading is 89 degrees, 54 minutes, and 50 seconds. Now adjust for the right pole, which is at 11.1 degrees. And move the crosshair here. You can see it moving up and down. We'll catch the top of that pole. And that reading is 89 degrees, 55 minutes, and 55 seconds. Okay, so there we have it. We'll look again at the poles through the camera. And this will be the end of it. Now just take a walk down to show that indeed nothing has changed. It's a beautiful day. Yeah, look out on the lake. Let's see here. See right over here, that's a view across the lake at Canada. Those high tension line towers are on the Canadian side of the border. I might note that on the Topcon theodolite, the resolution is in the minutes is 5 minutes. It goes in 5, or not minutes, but 5-second increments. So there isn't any way to resolve less than 5 seconds. So again, here we go, looking at our poles, that they're leaning. And we'll look at them from yet another angle. Get myself a line that is tangent, or not tangent, but perpendicular at right angles to the line of sight. I have that marked out here, so let's get that. Okay, there we are. So there's our poles leaning or tilting away from vertical. The center pole is the vertical pole. The right pole is leaning at 11.1 degrees, and the left pole is leaning so I'll just back off on this. We'll see if we can determine that the poles are tilting. From this vantage point, I'm about 50 feet away, and I can't tell, other than looking at the tops, that the poles are tilted away from me. There's just no way to determine that unless you look at the tops. They just look vertical. Back off again. Now zoom in. There's just no way to determine that there's a tilt to the left and the right pole, other than looking at the tops. You see a bit of a height difference because of the tilting or the leaning away. Again, if I cut the tops off, you can't tell that there's any lean at all. Again, I'll just continue backing up here. I'll do it again. Okay. Just no way to tell there's lean. Now cut the tops off again. There. Well, that concludes the test on the ability for us to detect structures tilting away as they would be on the surface of a sphere like the Earth. Here is a summary of the raw data that was accumulated using the Topcon theodolite that you just saw the video of. Here's the pertinent information. Here is the observer GPS coordinates, 48.61385 degrees north by 93.0 or 30806 degrees west. The pole GPS coordinates, 48.61378 degrees north by 93.30622 degrees west. Now, keep in mind that GPSs have certain amount of uncertainties also, and with my GPS I've determined over the years that this is plus minus 8 counts on this digit on the latitude, and it's plus minus 12 counts on the last digit in the longitude. Now in the latitude measurement, each count on the last digit represents about 3 feet, and on the longitude it's about 2.4 feet. So you can see that we have an uncertainty of about 30 feet in determining positions with the handheld GPS on the latitude, and it's about 30, about the same thing, or around 30 feet uncertainty in the in the GPS coordinates. And if you think your GPS positioning instrument is better than this, is you can easily fool yourself, and the easy way to check to see how accurate your GPS is take your GPS, go out, find a you know, a tree, or just put a mark on the ground, note your readings, and then turn your GPS off and turn it back on. Let it reaccumulate the satellites and see what your position is. Then you'll find that it isn't the same as what it was before you turned your GPS off. And then another test you can do is note the readings at a spot, put a stake in the ground, then walk maybe an eighth of a mile away, enough to make the GPS start reaccumulating data, and then walk back to the spot and look at your reading. You'll see that it doesn't come back to exactly the same reading. And that's because of the uncertainty in the GPS. Now, the distance to the poles measured by the theodolite total station was 441.38 feet, which is 5,297 inches. The temperature at the theodolite, where I'm making my observations, was 28.2 degrees Fahrenheit, and at the poles it's 28.7 degrees Fahrenheit. I monitored this throughout the afternoon, and it really didn't change between the two positions by more than a half a degree. And it really doesn't matter any refraction or anything, because what I'm making are differential measurements. When you make differential measurements, the refraction gets subtracted out. For example, if I'm measuring from an observer, I'm measuring the heights of these poles angularly. If the light ray bends, it's going to bend about equally to the two poles. So the difference, what we're doing is a differential measurement, getting the angular measure to this pole and the angular measure to this pole, subtract them off, so the refraction cancels out. So it really doesn't matter, but I took the temperature data anyway. Now, to get the tilt angle, what I did is, once a pole was adjusted, we have the vertical pole, which is the center pole. If I had the three poles lined up, the center pole A was always vertical. It always remained perpendicular to the earth. B is the left pole, C is the right pole. So after the poles have been set up, we have a vertical pole, and then one of the poles is tilted. And then what I did is I measured the center to center distance between the poles, and by using trigonometry we get what the angle theta is. That's much better and more accurate than trying to set up the angle, say, with a protractor and lining the pole up with a angular measure on a protractor. I found that that was very difficult to do. Even though I made a big protractor on a huge board, it just didn't work out very well. This is a much better way of doing it, is once you tilt the poles, measure the distance between them, and then use trigonometry to compute what the tilt angle is. Because if you know what the difference in the separation distance between the tops of the poles, and you know the height of the pole H, which is 120 inches, then the tilt angle is the arctangent of the separation distance divided by 120. Now, so here at the observer we have the theodolite, and what we're measuring with the theodolite are vertical angles. That is, the theodolite, all theodolites measure 0 degrees when they're pointed downward towards the center of the earth. That's 0 degree measurement on vertical angles with a theodolite. And then you measure a positive angle. The positive direction is as you swing up towards horizontal. Perfect horizontal or tangent to the earth will be at 90 degrees. And then if you're pointing the theodolite straight up, it's 180 degrees. So that's why all the angles look like they're near 90 degrees, because the theodolite measures from pointing downward. And this is called a vertical angle. So we make 3 angle measurements. I did 2 test adjustments. In the first test adjustment, I kept the center pole vertical and then tilted the left and the right poles. And then with the theodolite, we measure the vertical angle to the top of the center pole, which is vertical, then measure the vertical angle to the left pole, which is pole B, and then measure the vertical angle to the right pole, which was pole C. And these angles, these are the vertical angles measured with respect to vector pointed to the center of the Earth. So we're just measuring these vertical angles. Well, what we're interested in, though, is the angular difference. So we have to subtract off the vertical angle from B, of B from A to get this angular difference, and we have to subtract off the vertical angle on C from B, or from C from A, to get that vertical angle, or that angular difference that we're trying to measure. We're trying to measure these height differences, so we need to know what these angular differences are between the reference pole, the vertical pole, and the pole that's tilting. So these are our differential measurements. We have to subtract the vertical angles. Now, the tilt angles, we have theta B is the tilt, well, that's not quite right. These angles aren't measured that way. Theta B is this angle. This is the tilt angle of pole B. And theta C is that angle for measure the tilt from vertical. Now, this is my raw data. We did two tests. This is test number 1. This is test number 2. I first adjusted the poles for test 1, made all my data measurement, then went back to the poles and readjusted the tilt angles on B and C. That's test number 2. So what we have here is a reference pole, the vertical pole. The vertical angle measured to that pole is 89 degrees, 54 minutes, and 15 seconds. The vertical angle to the left pole, B, is 89 degrees, 57 minutes, 15 seconds. And to the right pole, 89 degrees, 54 minutes, 25 seconds. Now, the separation distance is the distance x between the vertical pole and the pole that is tilted. And of course, there is no difference between the vertical pole and itself. Here are the inches for the separation distance on pole B, the separation distance on pole C from the vertical, and then using the arctangent of x over 120, we can compute what these tilt angles are, and these are the tilt angles. So in the first test, pole B was tilted at 15.71 degrees. The right pole, C pole, was tilted at 2.68 degrees. Now, the angle phi, which is the apparent angular difference between the heights, these are our phi angles. So to get this angle here for pole B, we subtract the vertical angle of B from the vertical angle of A, or the other way around, either way. So if we subtract this from this, we see 57 minutes, 15 seconds. If we subtract 54 minutes, 15 seconds, we get exactly 3 minutes, which is 0.05 degrees. And the same thing for the right pole. To get angle phi, we subtract the vertical angle of the reference pole A from that of pole C, or the right pole. So 54 minutes, 25 seconds, and we subtract 54 minutes, 15 seconds, so we get 10 seconds. And that's what we have. And this is 0.00277 degrees. So you see that these perceived angular differences between the pole heights are very, very small angles. And you can imagine what it might be out at several kilometers or several miles. Here we're only dealing with 441 feet. Now, on the second test, the same sort of thing. I went back, I readjusted the right and the left pole angles, and then we measure the vertical angles. But you'll notice here that the vertical angle for the reference pole is slightly different. They're off by 10 seconds. So what happened there is I was fighting the wind. A gust came up after I'd made my measurements and knocked things over, and I had to reposition the vertical poles, and obviously I couldn't get it exactly set up. I mean, to have a 10-second difference in the vertical angle means a very, very slight difference in the actual base. I had to tap down the base so it moved the pole a little bit lower than it was previously. So anyway, here are the angular measures, the vertical angle measurements for the right and left pole and the center pole. And then again, I measured, once the poles were set up, we measured the separation distance X. Here are the separation distances, and then computing what the tilt angle is from these separation distances, and given the height of 120 inches. For the left pole, B pole, we get 5.59 degrees, and for the right pole, 11.8 degrees. So in the two tests, the poles, we had tilt angles of 2.68 degrees, 5.59 degrees, 11.08 degrees, and 15.71 degrees. And these, again, are computed just by taking differences of the vertical angles. For pole B, if we subtract this number from this number, we get 25 seconds. And if we subtract this number from this number, we get 1 minute and 30 seconds. And that is 0.025 degrees. And then using that number, these numbers for phi, we will calculate this tilt angle and compare it with what we actually measured just by using the separation distance. And I'll give you those numbers now. I've built another table here based on the raw data that we accumulated with the Topcon theodolite. If you'll notice that this column here is the same as this column. What this is the tilt angle computed from measuring the separation distance between the poles and just using the separation distance measured in inches, divide by 120, and then take the arctangent. That's what this computation is to give us the tilt angle. That's a direct measurement. Then this column here is a copy of this column, which gives us the tilt angle of the perceived height differences measured from a distance at 441 feet away using the Topcon instrumentation. So this angle is measured from a distance of 5,297 inches, and then we use the equation that to get the theta, the tilt angle. The tilt angle, remember, is K times the square root of this angular measure of the perceived height difference of the poles. And then the K is the value that I gave you before, which is 71.1215. If K equals 71.1215. That's our K value that's used in here. So what I'm doing then, from this column, is I'm taking this angular measure, multiplying it by this value to get the tilt angle. What I'm trying to do now is get what the tilt angle is by measuring the height difference of the poles and using that angular measure and the distance out and knowing the heights of the poles, is see if we can compute using that angle to get a tilt angle that's going to agree with the direct measurement. And you can see that they agree quite closely. If I subtract this measurement from this measurement, these are the errors that I'm getting in degrees between a direct measurement and an indirect measurement by measuring the angular difference in the heights. Now, this delta theta c is a theoretical uncertainty given that the TOPCon can measure to an accuracy of 5 arcseconds. So this is the expected level of uncertainty. Well, if I have a good measurement, this difference between the direct measurement and the computed measurement should be less than this number. This is the theoretical uncertainty, and we can see that indeed these numbers are less than the theoretical, except for this one. This one's almost a little bit above the theoretical limit, and the reason for that is that this measurement is at basically the limit of the TOPCon. If you look, this is C1. C1, we're getting an angular measurement here on phi of 10 seconds. Well, the best the TOPCon can do is 5 seconds, or arcseconds, and so the thing is I could have very well been off just by one of the counts on the last digit. I did notice that it was very difficult to get set. Just a little bit change would give me a 5 arcsecond difference. So this one, of course, is a little bit suspect because of such a small angle that we're trying to measure. I'm trying to resolve this 2.68 degrees with an angular measurement of only 10 seconds, 10 arcseconds. So it's not surprising that we might be a little bit off there. And if I go ahead and say if I've adjusted, if this was actually 5 arcseconds rather than 10 arcseconds, then the measured value for the for phi in figuring this number out, rather than coming out to 3.74, the number would have been 2.65, which would be in very much of agreement here. So just a 5 arcsecond changes us from 3.74 to 2.65. So when you're at the measurement limit of the instrument, you can pick up a lot of errors, and so this particular one is just a measurement that has potentially a lot of error just because you're at the limit of the instrument. Now, so what we can see here then is that the technique of measuring the angular difference in the perceived heights and knowing the distance to the poles can give us a very accurate measurement of the tilt angle. And it is possible to do it using precision instrumentation. Again, these are the angular height differences measured with a precision piece of equipment. And here, we're well below or at the limit of what we could ever do with the eye. The eye has a resolution limitation of 0.02 degrees, and here we're at that limit there. We're a little bit above the limit there, but very definitely below the limit of the eye on these two measurements. And the chances of you being able to line things up without a precision piece of equipment with precision crosshairs on optics, you'd never be able to do that with a camera. But anyway, what this goes to show is, if you look carefully at my videos, you're going to find it's very difficult to tell which of the poles is tilted. We had 4 different tilts. We had tilt at almost 16 degrees, around 3 degrees, around 5.5 degrees, and 11 degrees. And you can go back, review the videos knowing these tilt angles, and see if there's any way that you can really tell that these poles are tilted. And keep in mind that these are tilts are considerably more than you'd ever find on the Earth for anything reasonable. Is again, if on the Earth you have a pole and another pole separated by 69 miles, this tilt difference is only 1 degree. And here we're dealing with angular tilts 10 times larger than what you would be able to have for any reasonable distances on the Earth. Like, this is going to be so much less if you dial it back. Say if we go back, have these poles separated by 6.9 miles, this would only be 1/10 of a degree tilt difference. So if we're at 6.9 miles, we'd have a tilt of 0.1 degree. You'd never, even with precision equipment like this, be able to resolve that. Anyway, I hope this video helps enlighten the idea of perceiving tilt on the Earth.